Welcome to our presentation on NoSQL databases versus SQL databases. Today, we will explore the fundamental differences between these two types of databases, their unique features, and how to choose the right one for your specific needs. In today's session, we will cover the following topics. We will start with an overview of SQL databases. Next, we will look at the overview of NoSQL databases. Following that, we will look at the detailed comparison of SQL versus NoSQL. We will also look at the use cases for each type of database. And finally, the key factors to consider when selecting a database solution for your project. SQL databases, or structured query language databases, are traditional relational databases. They organize data into structured tables, which makes them excellent for applications where data integrity and security are crucial. Common examples of SQL databases include MySQL, PostgreSQL, Microsoft SQL Server, and Oracle. SQL databases, also known as relational databases, have several key features that make them suitable for specific use cases. These features include: first is technical support. SQL databases offer robust technical support and extensive documentation, making it easier for developers and users to troubleshoot and optimize their databases. Examples of SQL databases include MySQL, PostgreSQL, Microsoft SQL Server, and Oracle. Next is open source. Many SQL databases are open source, meaning they are freely available for use and modification. This allows for a more collaborative development environment and a wider range of customization options. Next is easy management. SQL databases have well-defined schemas and structures, making it easier to manage and maintain the database. This is particularly useful for large-scale applications where data integrity and security are critical. Let's move on to high availability. SQL databases are designed for high availability, ensuring that data is always accessible and up to date. This is achieved through features like automatic failover and replication. Next, let's look at vertical scalability. SQL databases can be scaled vertically by adding more power to the existing machine, such as increasing the CPU, RAM, or storage capacity. This makes them suitable for applications that require high performance and can afford the additional costs associated with vertical scaling. Next is security. SQL databases offer strong security features, including user authentication, access control, and encryption. This ensures that sensitive data is protected from unauthorized access or manipulation. And finally, portability. SQL databases can be easily ported across different operating systems and environments, making it easier to deploy and manage them in various contexts. Moving on to NoSQL databases, which stand for not only SQL. These are non-relational databases designed for high scalability and flexibility. They are ideal for handling large volumes of unstructured data. Popular examples include MongoDB, Cassandra, Redis, and Couchbase. NoSQL databases, on the other hand, have different key features that make them suitable for other use cases. Let's start with high scalability. NoSQL databases are designed to scale horizontally, meaning they can handle large volumes of data by distributing it across multiple servers. This makes them suitable for applications that require high performance and can benefit from distributed architectures. Next is big data capability. NoSQL databases are well suited for handling big data, as they can store and process large amounts of unstructured or semi-structured data. This is particularly useful for applications that deal with complex data types or require real-time data processing. Moving on to high availability. NoSQL databases also offer high availability, ensuring that data is always accessible and up to date. This is achieved through features like automatic failover and replication. Next, we have easy replication. NoSQL databases make it easy to replicate data across multiple servers, ensuring that data is available even if one server goes down. This is particularly useful for applications that require high availability and fault tolerance. And finally, fast performance. NoSQL databases are optimized for fast performance, making them suitable for applications that require real-time data processing or high throughput. SQL databases use a relational data model, which is based on tables and rows. This model is well suited for applications that require complex relationships between data and strict data integrity. In contrast, NoSQL databases use various data models, such as key-value, graph, column family, and document models. These models are more flexible and can handle unstructured or semi-structured data, making them suitable for applications that require more agility and scalability. Let's first look at SQL data types. First is relational. Relational databases organize data into structured tables with rows and columns, where each row represents a record and each column represents a specific attribute or field. Tables can be linked through foreign key relationships, enabling complex queries and data integrity enforcement through constraints. For example, in a relational database, you might have tables for customers, orders, and products, where relationships between these tables are defined by foreign keys linking primary keys. Next is analytical. Analytical databases, also known as OLAP, online analytical processing databases, are optimized for complex analytical queries and data warehousing applications. They typically use multidimensional data models such as star or snowflake schemas, allowing efficient analysis of large volumes of historical data. For example, a data warehouse for a retail company might use an analytical database to analyze sales trends, customer behavior, and inventory management across multiple dimensions like time, geography, and product categories. Now moving on to NoSQL data types. First is key-value. Key-value stores store data as a collection of key-value pairs, where each key is unique and maps to a corresponding value. This data model is simple and efficient, making it suitable for caching, session management, and distributed data storage. For example, Redis is a popular key-value store used for caching frequently accessed data, managing user sessions, and implementing distributed locking mechanisms. Next we have graph. Graph databases represent data as nodes, edges, and properties, allowing the storage and querying of interconnected data structures. This data model is ideal for applications with highly interconnected data, such as social networks, recommendation engines, and network analysis. For example, Neo4j is a graph database that allows users to model and query complex relationships between entities, such as relationships between users in a social network or dependencies between components in a network infrastructure. Next, we have column family. Column family databases organize data into columns grouped into column families, where each column family contains multiple rows. This data model is optimized for write-heavy workloads and allows efficient retrieval of large datasets with low latency. For example, Apache Cassandra is a column family database designed for distributed, highly available, and horizontally scalable data storage. It is commonly used in applications requiring real-time analytics, IoT data management, and time series data processing. And finally we have document. Document databases store data as flexible, schema-less documents, typically in JSON or BSON format. Each document can contain nested structures and arrays, providing flexibility in data representation and allowing developers to store and retrieve data in its natural form. For example, MongoDB is a document database that stores data in JSON-like documents, making it suitable for content management systems, real-time analytics, and applications requiring dynamic schema evolution. Let's delve into the comparison between SQL and NoSQL to understand their distinct characteristics and use cases. First aspect is data model. NoSQL databases offer a variety of data models, including document-oriented, key-value, and column family. These models provide flexibility in how data is structured and stored, allowing us to adapt to different types of data and application requirements. On the other hand, SQL databases are based on a relational data model. This means data is organized into structured tables with predefined schemas. Each table represents an entity, and relationships between tables enforce data integrity. Next aspect is schema flexibility. NoSQL databases are known for their schema flexibility. They allow us to store data without a predefined schema or with schemas that can evolve over time. This flexibility is particularly useful in scenarios where data schemas may change frequently or where we need to store diverse types of data. In contrast, SQL databases enforce rigid schemas. This means that data must adhere to predefined structures and relationships. While this can provide strong data integrity and consistency, it may also be less flexible in situations where data structures are subject to change. Next aspect is scalability. NoSQL databases are designed to scale horizontally, meaning they can easily handle increasing loads by adding more servers to the database cluster. This makes them well-suited for applications with growing data volumes and high traffic. SQL databases, on the other hand, typically scale vertically, which means increasing the resources, such as CPU, memory, or storage, of a single server. While vertical scaling can be effective to a certain extent, it may become cost-prohibitive or reach hardware limitations as the database grows. Next aspect is performance. NoSQL databases are often optimized for high performance, particularly in scenarios with read and write-heavy workloads. Their distributed architecture and flexible data models enable efficient data retrieval and manipulation, making them suitable for real-time applications and analytics. While SQL databases can deliver high performance for many use cases, they may face scalability challenges with massive datasets or complex queries. Additionally, the overhead of enforcing relational integrity and ACID properties can impact performance, especially in distributed environments. Next aspect is consistency. NoSQL databases often prioritize availability and partition tolerance over strong consistency. They may employ eventual consistency models, where data updates are propagated asynchronously and may take time to reach all nodes in the system. This relaxed consistency can result in faster response times but may lead to temporary inconsistencies. SQL databases, on the other hand, provide strong consistency guarantees through ACID transactions. This ensures that transactions are executed in a reliable and predictable manner, maintaining data integrity even in distributed environments. However, enforcing strong consistency can impact system performance and scalability. Next aspect is query language. NoSQL databases often have limited query capabilities compared to SQL databases. Many NoSQL databases offer proprietary query languages optimized for specific data models and use cases. While these languages may be sufficient for basic operations, they may lack the expressiveness and flexibility of SQL. SQL databases use a standardized query language, SQL, which provides a rich set of features for querying and manipulating relational data. SQL is widely adopted and supported by various database systems, making it familiar to developers and enabling complex analytical queries and reporting. Next aspect is ACID properties. Some NoSQL databases sacrifice ACID properties, that is atomicity, consistency, isolation, durability, in favor of scalability and performance. While this trade-off allows for greater flexibility and scalability, it may introduce risks such as data inconsistencies or loss in certain failure scenarios. SQL databases prioritize ACID properties, ensuring that transactions are atomic, consistent, isolated, and durable. This provides strong guarantees for data integrity and reliability, making SQL databases suitable for applications with stringent consistency requirements, such as financial transactions or e-commerce systems. Next aspect is transactions. NoSQL databases may offer limited support for transactions, especially in distributed environments. While some NoSQL databases provide mechanisms for handling transactions within single nodes or partitions, achieving distributed transactions with strong consistency across multiple nodes can be challenging and may require additional application logic. SQL databases offer strong support for transactions, allowing multiple operations to be grouped together as a single transaction. ACID properties ensure that transactions are executed reliably, even in the presence of failures or concurrent access. This makes SQL databases well suited for applications requiring data integrity and consistency. Next aspect is horizontal scaling. NoSQL databases are typically easier to scale horizontally due to their flexible data models and distributed architectures. Horizontal scaling involves adding more nodes to the database cluster, allowing the system to accommodate increasing loads and data volumes without significant performance degradation. While SQL databases can scale horizontally to some extent, they often require additional measures such as partitioning to distribute data across multiple servers. Vertical scaling, where resources are added to a single server, is more common in SQL databases but may have limitations in terms of scalability and cost. Finally, let's look at cost of maintenance. NoSQL databases generally have lower maintenance costs compared to SQL databases due to their simpler architectures and flexible schemas. With fewer constraints on data structure and fewer dependencies between entities, NoSQL databases can be easier to manage and scale, resulting in reduced maintenance overhead. SQL databases often require more maintenance efforts due to their complex schemas, normalization requirements, and the need for managing relational integrity. Additionally, licensing fees for commercial SQL database systems may contribute to higher maintenance costs, especially in enterprise environments. Let's delve into some specific use cases for SQL and NoSQL. First, let's look at the SQL database use cases. Firstly, financial applications. SQL databases are commonly used in financial institutions for managing transactions, accounts, and financial data with strict consistency and reliability requirements. Next is enterprise resource planning, ERP, systems. ERP systems integrate various business processes and departments within an organization, utilizing SQL databases to store and manage structured data such as inventory, sales, and human resources information. And finally, e-commerce platforms with complex relational data. E-commerce platforms often deal with complex relational data structures, including customer information, product catalogs, and order management. SQL databases are suitable for handling these relationships efficiently and ensuring data integrity through ACID transactions. Now let's look at NoSQL database use cases. Firstly, big data analytics. NoSQL databases are well suited for storing and analyzing large volumes of unstructured or semi-structured data generated by IoT devices, social media platforms, and other sources, enabling real-time analytics and insights. Next is real-time web applications. Real-time applications such as chat applications, gaming platforms, and social networking sites benefit from the high scalability and low latency performance offered by NoSQL databases, allowing rapid data ingestion and retrieval. And finally, content management systems handling diverse data types. CMS platforms often deal with diverse data types such as text, images, videos, and user-generated content. NoSQL databases provide flexibility in schema design and scalability, making them suitable for managing and delivering content efficiently across various channels. When selecting between SQL and NoSQL, several factors come into play. Let's explore these considerations in detail. Firstly, data structure and complexity. Assess the nature of your data and its complexity. SQL databases are well suited for structured data with complex relationships, while NoSQL databases excel with unstructured or semi-structured data, offering flexibility in schema design. Next, we consider scalability requirements. Determine your scalability needs. NoSQL databases are inherently designed for horizontal scalability, making them suitable for handling large volumes of data and distributed systems. SQL databases, on the other hand, may require vertical scaling or sharding for horizontal scalability. Moving on to consistency requirements. Consider the consistency requirements of your application. NoSQL databases often prioritize availability and partition tolerance over strong consistency, offering eventual consistency models. SQL databases provide strong consistency through ACID transactions, ensuring data integrity but potentially impacting scalability. Next is query flexibility. Evaluate the flexibility of your querying needs. SQL databases offer powerful querying capabilities with the standardized SQL language, suitable for complex relational queries and analytics. NoSQL databases may have more limited query capabilities, often relying on proprietary query languages or simple key-value lookups. Next is transactional needs. Determine the level of transactional support required by your application. SQL databases provide strong support for ACID transactions, ensuring atomicity, consistency, isolation, and durability. NoSQL databases may offer limited support for transactions, prioritizing performance and scalability over strict transactional guarantees. Finally, budget and maintenance capabilities. Consider the financial implications and maintenance overhead of your chosen database solution. NoSQL databases typically have lower maintenance costs due to simpler architectures and flexible schemas, making them more cost-effective for certain use cases. SQL databases may require more maintenance efforts due to complex schemas, normalization, and potentially higher licensing fees for commercial solutions. And with that, we've reached the end of our presentation. We hope you've gained some valuable insights. If you have any further questions or would like to explore more, please don't hesitate to leave a comment. Thank you for your time and attention. Please consider subscribing. Your support means the world to us at Consultant Bot. Every like, subscribe, and share helps this channel thrive, and it truly means a lot.